Welcome to this tutorial of the Kratos application. This is the 8th tutorial of the series, and in this one we continue talking about advanced options using the ROM manager. We will use the structural mechanics example, so these are the requirements if you want to follow the exercises. So we will talk about a linear or nonlinear decoder in this video. This what it means is, okay, these are the converged and non-converged solution and that we were discussing in the last video. Of course, this S matrix, the snapshot matrix, will independently of whether it contains converged and non-converged, this will still hold. So I will have number of degrees of freedom, that's the number of columns in this matrix, and if I have non-converged solutions, I will have more columns. But in any case, if I pass this matrix S here to a linear algebra operation called the SVD, and I pass also this epsilon, which is the tolerance of truncation, I will get this is a matrix that has the same number of rows, so number of degrees of freedom, and depending on epsilon, so if I put, and also depending on the nature of the data contained in S, but if I want my reducer model to be accurate, then I should put a small value of epsilon. So if, for example, I had here, sorry, let's say if I put epsilon equal 1 e to the minus 8 and I get n equals 10, so that's okay. That means that this capital N, that's the number of columns in this basis matrix, that dictates how fast my reducer model will be. In some way, this dictates if my reducer model will be able to capture enough of the information. And I want it to be small so that my reducer model is fast. But let's imagine the scenario in which I said epsilon equals 1 e to the minus 6 and I get n equals 1000. So in such a scenario, I would get that in order for my reducer model to be accurate, I need to have a lot of columns in this basis, and therefore my reducer model won't be fast. This is a possible scenario, and in order to do that, in the literature, people decided to split this basis matrix in cases where n was large. So if n is large for small values of epsilon, what I can do is simply split this. Probably I can show before the linear case, which is the linear decoder, where to set it, and this is the example. This is the structural example, and let us go to the main Kratos.py. This is the example that we showed in the previous converged and non-converged solutions. So if I just launch it as is, we saw that we were getting an error. And let me see if I'm getting, right now I'm using the non-converged solutions and I'm storing them with this flag and using them with this other flag. And we saw that the error was of the order of 0.0021. So I can change this value of epsilon in order to get a more accurate solution. And this value of epsilon, if you go to the ROM manager parameters, it's set by default, since we didn't change it, it's set by default to 1 e to the minus 5. So that's the value of epsilon that we have here. And with that value of epsilon, let me go here to the ROM data folder, and inside there's a ROM parameters.json file. So we have 6. So n over here equals 6 when I set 1 e to the minus 5 here. Let me set here to 0, or numerically 0, and see how many columns I have in that matrix. So if I set that to 0, so I will go here and set this, it's in the ROM field, let's put here 0. And if I launch this, I'll get, as you can see, this is numerically 0, so I get 5 e to the minus 11. So my reducer model now, without changing the data that I am using, I'm using non-converged and converged, so I got a matrix like this one, and by passing 0, I got Before it was 6. Now let's see how many columns I have. So I have 10. So with a basis of 10, I am able, using a single case and the non-converged solutions, to get this level of accuracy. So you saw that by changing only this parameter in the ROM manager, I get a much accurate solution. Sometimes, I mean, if this number is small enough for your applications and you get good speedups with good accuracy, then that might work for you. The other thing that is already implemented in the ROM manager is a nonlinear decoder. The nonlinear part goes like this. So rather than having to use a single basis matrix, we can split it, and by splitting it, I consider, rather than only one capital N, I consider NINF and NSUP. And if NINF is small enough for my application, this is the one that will dictate how fast my reducer model will be. And this one will help me still capture the behavior that I would capture using both of them. So I will have the speed up of this, and I should have the accuracy of using both. Let us see how it goes. So the first step is the same. I pass a snapshot matrix to the SVD, I get these bases, and then I split it. And then in order to get an approximation, I will get my reducer model using this NINF, and I will use a neural network for this second part, for the approximation of what this would help me to approximate. If you want to see the technical details, you can follow the QR and see the scientific paper explaining this. But that's the idea, and I will now show you how to set up the parameters using the ROM manager. So I come here and I look for ANN enhanced settings. So let me copy all of this and go to here. So I should paste it in the ROM field. So I come here and go to the ROM field here, and let me put a comma here in order for the JSON parse to work, and that's, I guess, good enough. Nope, I need to do this. So that should work. So what are these parameters? Modes that dictates NINF will finish in this one, and NSUP will finish in this one. So I saw that by using true in the non-converged solutions and true, well, this one can already be false. This only works for storing the non-converged solutions. The one that we care right now is this one. So if this one is true, we saw that we had 10 modes. So the maximum that I can put here is 10. So NINF should be 5 for this case, and NSUP 10. So from 6 to 10. So that's the number of modes on each of the ends. So let me just go here. So right now this one should have columns 1 to 5, and this one would have columns 6 to 10. And then I need to choose the number of neurons inside. So right now it's set by 200 and 200. So it will be a matrix. Sorry, it will be a neural network with 5 neurons, then 200, 200, and in the end 10. Then batch size and epochs. This is normal terms in neural networks training. Then neural network gradient regularization. This is something we're experimenting with, and it should improve the stability of the training, but it kind of slows down the convergence. Then we have here scheduler, base learning rate, and additional parameters. So the schedulers that we are working with is this SGDR, and this basically says what the minimum learning rate is. I mean, these additional parameters, if you use this scheduler, will be the minimum learning rate and the periods, and every 400 passes through the data, the learning rate will decrease by a factor of 10 until it reaches this one. So these are very specific parameters about the training of the neural network. And if you want to see the implementations, you can go here in the in ROM application, Python scripts, and there's a neural network trainer, ROM NN trainer, and this one contains, it is implemented using TensorFlow and some Keras models. You can have a look. We might change this since we are modifying this actively right now, but these are very specific, so in order to be safe, you can thing is const, and by this you just keep the learning rate as is, or through the implementation, through the launching of the training. So let us keep I just changed this mode so that they match the size of the available matrices, in this case the base matrix. And this is training. Retrain if exists. This is a parameter that dictates whether I will launch it again, because as we saw in the previous videos, the database, what it allows me to do is to not rerun something that it already exists. In neural networks, it might sometimes be interesting to rerun it, since it might start with some different random weights, and you can reach to some optimum that you had not previously. So since this is it's not a since there's a randomness introduced, there's this optimization process of neural networks. So if you put true here, you will probably find a better solution if you run it 10 times and then you choose the best model. So return if exists, that's it. If it is false, it will run it once. If you put true, it will run it many times, and you can choose then your best model. If you are running this in the online stage, you know, with the run ROM, so rommanager.run ROM, you need to input here your best model based on the error that you got. That's a long way of explaining it, but that's only if you need this kind of model. Let us launch it with this, but of course we have set the NN enhanced settings right now, but if we just put run and debug, it will not use it because we are not telling it to use it. The decoder type is one of the parameters that goes. Let me go to Python scripts and ROM manager. So the decoder type, if I go to the default parameters here, so this is projection strategy type of decoder. So this is linear, oops, and here so the main field type of decoder. Linear, that's the basic one. Then an enhanced. This way I'm telling the ROM manager that I should use this enhanced, and then here we will be adding different types of decoders, for example quadratic and others that we have been working on, but as of now there are two options. If I put train run the debugger, so I should be able to see here. So it doesn't like something, it doesn't. So this should work already. Let's see. Okay, yes, when I launch the enhance, I should pass not only a mu train, but also a mu validation. This is something that has to do with, well, let me put the same. Of course, you wouldn't want to do it the same. I'm just showing the architecture. So the cross validation is used inside to check the error not with the training parameters, but with the validation ones. So I need to pass it. You can check the implementation there in the ROM manager, but once it does this, it comes and it launches the training of the neural network using TensorFlow. I put 800 epochs, so maybe I should have put less. So let us wait, and while we wait, I can probably show you where it's this in the ROM manager. So it's the method, the fit method here. So the fit method, as you can see, it takes two arguments, mu train and mu validation. This mu validation is only used inside the training of the neural network. So if you see, if you go for NL enhanced, then it uses it. If it is linear, it doesn't use it. If it is something not linear or not NL enhanced, at the moment we don't have it in the master, so we are working on putting here quadratic and other types of decoders. But let me just go here back to the raw manager and see. Okay, it finished the 800 epochs. It gave me some measures here that you can see on the snapshot, on the how it does with POD, without POD, and just for the comparison. That is, I get this value of the NL enhanced using POD only, gives me this. Using the POD, that is the linear method, only with the lower modes, with the NINF modes, would give me this. So this is the best I could do using all of the modes, and I'm getting this one. So this is a measure of this is as good as it can be. This is how it is improving, and this is the linear method using only the NINF. That is, using only this, I get 1e to the minus 5. Using these two, I get 1e to the minus 7. But using the complete linear method, but with whole modes, I get 1e to the minus 15. So I can still improve my neural network so that it captures better the behavior. So right now I am not inputting. You know, this, you need to get the optimum of your neural network, but this is a topic of a different discussion. So by now, using this neural network enhanced POD, I got this error. That's it. So of course, if I change something here, if I increase the training set, I increase this, then I could improve it and try to reach something closer to the linear, but using, of course, much lower number of NINFs. Let me just finish this. I know this might be a dense video, but let me just finish this by saying why we call it a decoder. And in the following video, I will show you how inside of Kratos these matrices are used. But for now, let me just say that Kratos inside the ROM application computes for me this little vector, and of course it has dimension capital N, as we saw here. It has dimension, at least for the linear case, it has dimension capital N. So if Kratos computes for me this little vector and I want to get that big vector that has a number of degrees of freedom, I need to decode it in some way, and the easiest way to decode it is linearly. So I use phi, which of course, you know, it has also a capital N columns. So by multiplying this matrix by that vector, I get a vector that is the approximation of the full order model. So Kratos inside will compute this little vector, and I will tell you in the next video how it does it. And we decode it using simply linear operation, that is a weighted sum of the columns of this phi, and that's it. That's the linear decoder. The nonlinear decoder, of course, at least this one that we have been covering in this video, is I will get inside Kratos a vector that has dimension NINF. So Kratos will give me this inside, it will compute that one. In order to decode it, I will get this part, which is exactly the same as the first one, plus a contribution coming from the multiplication of the matrix discarded in the first one, if you will, of this second matrix, and the weights, that is the vector that will be multiplying this matrix, will be coming from the neural network. So we only compute one little vector, and then this little vector will pass it to the neural network and get a vector of dimension n sub, and that is the weights of the columns, right? So I get a decoded version through this decoder of this little vector that Kratos computes for me. So that's why just the jargon, trying to explain the jargon decoder. So Kratos will compute this vector either dimension capital N or dimension capital NINF, and then I transform that vector into this vector of dimension n number of degrees of freedom through some decoding operation, which is For the non-linear case, this one involving a neural network or just a simple linear operation. That's it. So that was a long video, but I hope we showed how to set it in the Kratos in the Enroll Manager and where the implementation is in case you want to go further. In the following video, we will be covering the different types of projection, Galerkin, LSPG, and Petrov-Galerkin. And in this one, we will show how inside Kratos this little vector is actually computed and the options that we have to compute it inside Kratos, which are that one, the LSPG, Galerkin, or Petrov-Galerkin.